Good morning. I hope you're fine. Last time we failed to have our Zoom first session because of the uncoordination that happened, but because of that, I thought of another option, and I want us to try out this one, and you let me know. I would love to know your feedback about this option. We are going to try out this channel and see how things go. I hope you can see them, you can be able to visualize the question very well. Sorry for that background noise. You know, we're just starting the whole thing, but I would love us to discuss this question number two. They're telling you the electric potential at points inside a long rectangular metal pipe whose cross-section has dimensions pi by pi and whose sides are grounded except the end x is equal to 0, which is maintained at a potential V0. So when x is equal to 0, this is the x-axis, this is the x-axis, this is the y-axis, this is the z-axis. So when they say x is equal to 0, you remain in the yz. That's why he has yz. So this is telling you that this side, there's a potential along here. The potential is V0. He has given us the boundary conditions telling you that when y is 0, you are in the xz plane. This one down below there is telling you that the potential is 0, and is telling you that when y is pi up here, the potential is also what? 0. Or in other words, you can say it is grounded. And it's telling you when z is 0, you are in the xz. So this arrow is representing that the potential there is 0. And when z is pi, that means you are here, is telling you that this side is also what? Is also 0. The potential along there is 0. So this one I've already explained, and it's telling you that as x tends to infinity, as x goes very far away, but in the positive sense, very far away, the potential tends to what? To 0. I want you to understand that this boundary condition is not the same as these ones. Here is telling you the potential is 0. The potential is 0 when z is 0. But here, as you are moving, as x keeps on increasing to a very bigger value, the potential keeps on dropping and it tends to 0. Okay? Tending to 0 is different from equal to 0. It keeps on reducing, but it just moves closer to 0, right? So we want to know the potential within the metal plate. Now, for us to solve this one, right, I want you to look at the boundary conditions. I told you the boundary conditions guide you. They are talking of x, they are talking of z, they are talking of what? Y. So for you to do this, remember, I want to show you something here. The first thing we need to know that the assumption is that always the potential, because now it is to those three parameters, it is always a product of the three terms. You remember that? I told you that the first assumption we make that the potential will always be a product of the three. And we are going to use the Laplace's what? The Laplace's equation, which is equal to that the square of the square of this del operator, the Laplace will always be equal to what? 0. Which means that you will have dv, the x plus dv dy plus dv the z, the whole thing is equal to what? 0. And we said we let, now because z is a product, we are going to substitute. We know v is a product of all these three, so we are going to put this here, back here, right? So when you put it back here, remember this one depends on z, x only. That means yz will be a constant, right? And you remain with only x. The x, this one should be small x, right? Plus this one will be now, you'll have x, you'll have the z, and here you'll have capital Y, and here you'll have small y, plus this one will remain with x, y. Now this one will be d dz squared. The whole thing is equal to what? To 0. Then the next thing I told you divide by the product, all of them. So you will see that you'll have when you divide by the whole of that, you'll have 1 over x dx, that plus 1 over y dy, that plus 1 over z, dz is equal to 0. Right? Now at this level, you'll see this is a function of x plus a function of y plus a function of z, and the whole of them is equal to what? 0. So this is where you start to let let this one now be z be a function, a square of a constant z, let this one be a square of constant of what? This is a constant of y, this one is also a constant of a square of a constant k, subscript x, such that when we add these ones, they still also give us 0, right? So you can have a statement like this, that you can have this statement that is equal to what? Is equal to 0. All right? If that one is captured now, this statement I have here, this statement is this statement that is here. All right? Now what we do, if we have let, because we have said let f this function f of z, this function f of z, we have called it to be a square of a constant k. All right? So which is the same here, and we have done the same thing for y and the same thing for x. All right? Now if we are to solve, you remember I told you that now we are here. This one I've already explained. From here, we can reduce this. All these ones, what is doing k squared is what I've done here, right? Now, if you have that, for example, if you have said you are going to start, the best way to understand it is that you are going to be starting from the, you are going to start, when you look at these equations, when you are solving them, you start from the right going to the left, move like this. From the right going to the left. So the first thing you can do is although here for him he started with the y. So because remember we have said that 1 over y dy squared, the whole thing is equal to, all right? So this one, for you to solve it, you can say that you can let, that's why he's telling you can let this constant, you call it a negative of m what? Of that constant, right? You can let it to be this, the square of a constant, you can give it a negative km squared. Remember I explained to you this thing that if, let me explain it to you here, that if we have, because remember I have k squared plus ky squared plus this is kz squared. If these, for all these constants to be 0, all right, we can say a constant plus a square of a constant plus, I beg your pardon, let me start it like this. Remember, we said that if we have these functions from here, this is a function of x, function of y, function of z. If all these functions are equal to 0, remember we said that this expression becomes hard. We cannot have these ones unless we cannot have a statement that when you add a function of y plus a function of z plus a function of z, the whole thing is equal to 0. This is impossible unless these are what? Constants. And we are saying we are taking a situation when the constants are squares. Square that one, and that is when we can have a case when these functions are constants. That's when we can have that the sum of them will be equal to what? To 0. Okay? Now, if you are going to solve this, right? If we let what we are doing, if we let that let kz be equal to a negative square of n, and we let ky squared be a negative of another number. We're just choosing other constants because we don't want to deal with these ones, right? We don't want to, k is common, so we want to give them different letters. That this constant of z, we are giving it a negative of n squared, and this constant of ky, we are giving it a negative of m squared, and I'm going to tell you why I'm giving them negatives, such that when you put these guys here, you will have f of x. Now, we have already called this one to be what? We have already called this one to be negative m, so it will be minus m squared. This one already we have called it what? N is equal to 0. This implies that f of x is equal to n squared plus m what? Squared. And when you put back here, this is when the expression that n squared, because if f of x plus f of y plus f of z is equal to 0. These are, and f of x, we have got it to be that f of y is negative of m, and f of z is equal to what? So that is when you can have the whole thing equal to what? To 0. Okay? So this statement to be true, these f of z and f of z should be negatives. Negative of a square of a constant. That's why we call them negatives, and f should be a positive of the sum of the what? Of the constants. Alright? Now for you, now we come back here. For you to solve, that is why we are saying if we have let that k of y to be equal to this and kz to be equal to that, this is the new constant, right? Now you'll be able to solve. That is what is here. That if you have let that 1 over y is equal to k squared y, but this k squared y is negative of what? This tells you that y is equal to negative m squared. All right? Now, for you to come to this equation you are seeing here, this equation that you are seeing here, it implies that you'll have that when you cross multiply and bring this one here, you'll have is equal to what? Is equal to 0. And remember last time I told you how we solve these equations. We solve these equations by letting you let y be equal to an exponential. Okay? I told you let y to be equal to an exponential. Alright? To an exponential of another number, maybe p of y. Alright? And I told you when you differentiate this one twice, when you differentiate it twice, you have p squared e py, right? And when now where there is this, you're going to write the whole of that. So this one is the one you're going to come and put here, such that you have p squared e py plus m squared. Already y you have called it ep y, and the whole thing is equal to what? 0. So you have created an equation epy p squared, and this is equal to what? So you can see p. So by letting this one, you are trying to generate a quadratic equation that you'll be able to do what? To solve, right? So p squared tells you it is a negative of m squared, and p will always give you square root of an exponential, a negative, I mean square root of a negative value to always give you I m. Alright, but because it is a square root, so the p values will always be plus or minus I representing the negative of square root of 1, and m. So that means that this y, the solution to y, is always now m plus or minus I m what? P, we have got p is now what? Plus or minus y, right? And I told you when you get these are complex, we call them complex what? These are complex roots. So if you see you're getting complex roots, then this one's going to be a trigonometric what? This one's going to be now a trigonometric function. That is why it's telling you that this one will give us a trigonometric what? Function that when you solve, so this one is irrelevant. The moment you see this and you see you can always get, when you solve this one you get complex roots, it's better you quote that's going to be a trigonometric what? Function. Now you can solve them at this level. That's why it's telling you that if y is a sine my plus that one. Now the boundary conditions, if you put in the boundary conditions at this level, that the boundary conditions, we are going to use the first one, that when y is 0, the potential is what? The potential is 0, right? So when you put in y, that means y is 0. When you put in 0, you'll have b will remain, right? B will remain, and this one, sine of 0 will be 0, all right? So you will see that b will be equal to 0. That's why it's implying that 0 is equal to b, or b is, yeah, it is here that this implies, this sign implies that b is equal to 1? 0. So this term will go away and only remain with that term. So the boundary conditions for v is equal to 0 at y is equal to pi. Now, remember our boundary conditions now has reduced. It has now come to y is equal to a sine m. All right. Now, if y is pi, y is what? 0. Y is 0. That implies that this is equal to 0 and this is a. This will be sine m what? M pi. All right. This implies that a is 0, right? If you divide it, you'll be having 0. So you remain with sine m pi is equal to 0. Okay. And if this is equal to 0, if this is equal to 0, this implies that m pi should be equal to the sine arc of what? Of 0. And now these ones, m pi, it will give you, you will start the values of 0. Sine of 0, they will have 0 as the first angle. Then the other angle will be pi. Then you'll have 2 pi. You'll have 3 pi, 4 pi, 5 pi, and so on. Okay, you see that? Now, what does that one tell you? It tells you that m pi, these ones can be, remember now this one, because this is like, these are integers, 0, 1, 2, 3, and so on. So it is giving you another value. You can use another value like p. I can call it n value. Okay, n where n is an integer. All right, so it will be n pi. All right, m pi is equal to n what? N pi. All right, so in other words, we are seeing m is equal to what? N. but I don't want to use n because somewhere they already used n. I can use a value like p, where p is an integer, right? P is an integer, because that one will go with that. So it tells you that this m value is always equal to the integer, but you don't want to take the integer of 0, all right? We don't want to take the integer because it will make all our solutions come to 0, all right? So this one tells you that m can be equal to, the value of m can be equal to p, where p, these are values 1, 2, 3, 4, 5, and so on from this, all right? Now, that one, which is here now, also for z, you do the same thing. Now, for z, I told you, z is this one. They have let it to be equal to that, so they are calling it a negative, all right? So it will follow the same sequence, right? It will follow the same sequence. And when you put in the boundary conditions, that when z is equal to 0, the potential to be equal to 0, you will see that d is equal to 0, and also to reduce to that one. So the boundary condition, when you put in another one that z is equal to pi, it will tell you, it will be giving you the same thing. You will see that n, you will see n is equal maybe to 2. That will be another. It will give you this, that n is equal to what? N is equal to 2, because it will be following the same trend as this one, right? You will work it out and see. So, what does this one tell you? Now it means that you have already used these 1, 2, 3, 4. You have used all those boundary conditions, right? Now, you will see that we have, they're talking equations 8.8 lead us to this. You remember when we had that, let me see it, we had it here. This one, this statement is the same as this statement that is here. So you want to find f of x. F of x will be n squared, this one, right? But remember, we had called it what? We had called it a square. Here we had let it to be a square. That's why he's saying that this k of x can be the square root, of n squared plus m what? Okay. All right. That's why this one comes in plus or minus. So the whole of this one can be equal to what? The whole of k. The best way to solve this one, if it's going to disturb you, because now you'll be having, we have seen that this kx is plus or minus the square root of m squared plus n what? N squared. You see that? But this value can be very big. You can say that let the whole of this value, I call it a letter m or l. You can call it l, whereby kx can be equal to l, but this l is the square root of, if you want to simplify, work, okay, such that you can have 1 over x, the x, this one, is equal to l, okay? So when you bring this on this side and you cross multiply, you have that d minus lx, this should be capital X, is equal to what? When you see it is a minus here, this one tells you that the solution is you are going to get what you call real what? You're going to get real roots. And when you get real roots, the expression will be x. The general equation will be x of x will be e, a constant, maybe you can call it a. It will be L of x plus b e L negative L of what? X. But remember your L is a square root of what? M squared plus what? N squared. So you can say x, this one can be a, you can take whatever you want to, which is simpler for you. Either you deal with the square root, okay, of x, small x plus b negative of n squared plus that squared, right? So you see that you can say either to use this one or you can say to use L, the n that is simpler for you. This is just a shortcut. Now, if we are going to put in the boundary, now we are going to put in the boundary conditions, right? The boundary conditions we are going to put in, they are telling you that the potential tends to zero. The potential tends to zero as x tends to be very what? Very big. As x becomes very big, right? So as x tends to be very big, I want to use a very simple, I don't want to use this one. I want to say that x is a, I've already told you, can be Lx plus be negative of L what? So if they are telling you the potential tends to zero when x also tends to what? Infinity. Okay? Now, what does this one mean? It means that x is equal to 0. We have this will be a. X should be a very big value. If you put in a very big value, L times a very big value, I don't know, you can take maybe 100 what? You try it on your what? On your phone, plus b negative of a very big what? I'm using 100,000 as a very big value. All right, it is exponential, right, of a very big value. All right, now it will tell you that exponential of a very big value, all right, exponential of a very big negative value, it will always be 0. All right, now that tells you that, and this one, exponential of a very positive big value, it is always what? 1. So you will see that you'll have a 0 is equal to a times 1 plus 0. This tells you that a is equal to what? Sorry, this one tells you that a, where what I've been explaining is that when you, I'm assuming that if you take a very big value, all right, this big value, and the exponential of a very positive big value is 1. We can approximate it equal to 1, but the exponential of a very negative big value will tend to 0. So that's why you'll have 0, this side will be 0, plus this is 1, tends to 1 times that one. So you'll see a is equal to what? 0. That's why it's telling you that as this one tends to 0, x tends to 0 as this one tends to infinity. This one is equal to what? 0. So it means that this term is going to go away, right? And your x reduces to, if now a is 0, your term you only have b e negative of what? X, which is the same as b constant. You can say this one negative of m squared plus n, all right, x. You remember your y had reduced to a certain constant a sine my. The z had reduced to a constant, maybe a constant c, as you see it, c sine n and z. So for now we are going first of all stop here, and now we are going first of all stop here. We have used all the boundary conditions. We have used all these ones, this one, that one, that one, that one, and this one. So the remaining boundary condition we have left with is this one. All right, and remember, when we are starting, the assumption you had was to assume, where did we start from? Like a paper. Yes, we started from here, that you assume that all these guys are a product. So you're going to multiply all these terms that we have got here. You're going to multiply them. But remember, these two, they give you the summation, all right? Remember, we said that I want us to first have a break here, that our potential Vy x squared is supposed to be a product of that. But remember, these two, m takes on different what? Takes on different values. So it will always be a summation. That is why if you're going to take a product, you'll see a product of all these constants will give you one constant, right? So you'll see that our v xy, we shall have these two summations. Then we have one constant. I don't know here in this book which constant did they use. They used am. Yeah, they use the constant am. X we got it as e, that exponential. I want to call it lx because I don't have space. Now y is sine my times z, which is sine n and z. So this is where we're going to start from. All right, and our interest is to know this constant. Remember, this one m runs from 1 to infinity. Here n runs from 1 to what? To infinity. First of all, we're going to stop here for today. I want you to give me some feedback if you have understood up to this level, where your L is m squared plus what? N. So you can use any letter. I want you to, I need your comments if you have understood from where we started from here up to where we have stopped here. All right, because the next part